Welcome again, everybody, to the Bioinformatics Bridge course in the 2024 session. So far, do people have any questions or any comments or any concern about anything? I guess this is that's a no. So I'm gonna go ahead and do a couple. Okay, Alexandra asked about instructions for the project. Today I'm gonna show instructions for the command. And as you talk to me by the end, because I have not put the instructions in the website, in the handbook yet. So talk to me, we can discuss, and I'll do my best to help people that want to present on the project, okay? But before talking about that, let's do the announcements again. We still are waiting for people to apply to the scholarships that we have. We have 4. There's still space if people want to apply. Again, we need US, at this time, we can only offer to US citizens, green card holders, or individuals with permission to work in the United States. If you feel you can benefit from one of the scholarships, go to this link that basically asks why will the scholarship help you, and you may get one of the scholarships. Does anyone have questions about this? Is there any questions about this? Okay. We will have a guest speaker this coming Wednesday. She's going to introduce machine learning for us. And I want to ask if we can start 2 hours earlier. Can we start 2 hours earlier? Who cannot join 2 hours earlier? Can you put it in the chat, or you just unmute yourself and speak? Victor said he cannot. Only Victor cannot be here. Victor, Rishima. No, it would be 2 p.m. to 3:50 p.m. Hannah. So only Victor and Rishima cannot attend from 2 p.m. to 3:50 p.m. Pacific time. If that is the case, Victor and Rishima, we always record the sessions. So if you have questions after recording the session, you can always email me and I can send the questions to Anna, or we can try to email her directly with any questions that you may have, because only the 2 of you cannot make it. Okay, yeah. I think I'll send out an official email because we only have 9 people here. I mean, probably less people than expected. So I'll send out an official email and see what other people might think. Okay. I already wrote some details to present on the command. Okay, it's here in the bioinformatics Bridge Course Handbook. So there, I prepared this list here. If people do not decide what they want to present on, I put here some commands that they can present on Friday. And your presentation should include the following: one slide defining the command. You can use technical language to describe the command, but also non-technical language explaining what the command does. One slide giving an example of how the command is supposed to work. And you can use an example from the code notebook with a screenshot of you using the command. One slide also giving examples of mistakes that occurred when you used the command, with the screenshot demonstrating the mistake that was shown in the R console. You should be prepared to spend less than 5 minutes walking us through the command. And please put your slides in the folder called presentations describing commands. There's an example of a command, of a presentation on a command here. The example here was the command head. You can take a look at this. And I want you to put the presentations in this folder here, presentations describing commands. This. Okay, so I would like for us to go ahead and give the progress update. Can you start, Alexandra?
Yeah, I'm doing pretty good. I completely finished, I'm completely caught up in the notes and everything. So,
Great. Claire? Claire, do you hear us? Okay. Can you write in the chat an update for us, Claire? Eric?
I'm honestly a bit behind. I had to miss class on Friday, and I've kind of been busy with a couple other things. I'm also taking some summer classes. So I am a bit behind, but I might have some time this week to catch up. And then I'm also behind on the notebook. I hadn't realized that we had to like update our notes or put together something to update. And I should be able to, but I should be able to catch up and definitely have that presentation for Friday.
Okay. No worries, Eric. So the purpose of this is just for us to be aware of where we are at and how we are doing. You do not have to worry so much about being the most up to date, but of course it's good practice to be updated in the materials. Yeah, so thank you for updating us. Rishima, do you want to give us an update now? Rishima?
Yeah, sorry. Yeah, I'm just finishing up the updates from like the last day, first week, like day 3, and I'm like almost done finishing that up. So I think it should be done by like either tonight or tomorrow. Yeah.
Thank you. Is it Hannah? How you say your name?
Yes.
Yes.
I'm finishing up my notes from Friday. So when I finish that, I'll be sure to upload it.
Okay, thank you. Is it only Victor that did not give us an update now?
Yeah. So I'm doing a little bit better now. I just like everyone else, I still need a little bit more to finish on from last class Friday. I just need to catch up on that and pretty much up to date with my notes.
Okay. Yeah, I also understand that for many people, this is all very new. So and a week is very little time to um, catch up on all of this. It's a lot of new information, so that's totally fine. So just make sure you follow the code notebooks and try stuff. I also think, not I also think, I also updated the exercises. Now we're going to go through some of these exercises by the end of today. Yeah, I think that would be all for now. We can go ahead and let's go ahead and get started on the notebooks again. So right now we are on the notebook 3. I called it data visualization. The title of this here is plots of the neuroblastoma data frame. By the way, I already uploaded videos to describe this part here. So the data visualization. So if we have to, for whatever reason, if you get stuck on any step here, that's fine. We already have the videos available where I go through majority of the steps here. All right, let's get started here. I already have our studio open, but it's in that one project. It's not what I want. I'm going to go ahead and restart my R Studio. I think we already did this on Friday. That was uploading the metadata object, but I do not know if, okay, I already have the object in my desktop, but I'm going to download it again. So I go to the data folder here, and I can download this metadata object, the R2 underscore GSC 62564 underscore GSVA underscore metadata. And I'm going to download it to my desktop. I'm going to ask it to save. I'm going to replace whatever is there. And that's it. And I'm going to copy this again. I think we already did this on Friday, but because I do not have my environment from Friday, I'm going to do the desktop part again, and then R2, metadata, enter, ILS now. I have this object in my environment. Let's do this very quickly. Right now, let's check what the class of the MICN status variable is. Its character. I need to make it numeric. So as numeric, I'm going to make the MICN as numeric. So this MICN is the gene expression, and the gene expression needs to be numeric. It must be numeric. I can check which class it has now, and it's numeric. That's what I need. I'm gonna skip this check the age of diagnosis step because it's something else. This has an error. This also has an error. So I'm going to go to the third chunk here. And in this chunk, we're going to take a look at the box plot of the MICN expression in the MICN status groups, in the MICN amplification status group. So this variable, the MIC-N status variable, informs us whether the child has MIC-N amplification or not, right? So just as a reminder, what I can do is I can copy this data frame. And let's check the MIC-N underscore status variable. Let's check what shows up. It shows up apparently 497 and 98. In this case, I believe this is 498 lines, because remember there are 498 patients. What happens if I use the word head here? It's showing to me only the very first 1, 2, 3, 4, 5, 6 elements in this data frame. Okay, let's just remind ourselves about the dimensions of this data frame. It has 498 lines and more than 25,000 columns. Okay, so when I remember that in R, when we use the $sign after the name of the data frame, we are referring to the column. This is a column, okay? And it's also, we can also call this a variable. And basically what this line is informing us is the MIC-N status of each and every patient, each and every one of the 498 patients. And it's informing us whether the patient is MIC-N amplified or MIC-N non-amplified. What we can do now is I'm going to go ahead and load the ggplot library. And I'm going to use this ggplot function. Remember, this is the data set. And then we are going to specify the x-axis and the y-axis. And this fill argument is going to color in different colors what using the MIC-N status variable. This geom underscore box plot is a function that I need to include to specify the type of graph that I want to plot, basically. So now I'm gonna copy this and I'm gonna paste it here. And now we can see a plot just like this one plot here, where we have the MIC-N status in the x-axis and the MIC-N gene expression in the y-axis. The MIC-N expression, again, is basically the counts, the number of counts of the MIC-N gene. And what we can see in the plot that we just did from the R studio, we can see that individuals that have MIC-N amplification have much higher counts of the MIC-N gene. All right. Can anyone think of the difference between MIC-N amplification and MIC-N expression? What's the difference between them? Can anyone guess what the difference is? Alexander just said that MIC-N expression is how the MIC-N shows, and by shows you mean how much of it is expressed, right? Yeah, that's right. MIC-N is the gene. The MIC-N status, it's actually an exam result. Like the doctor would run an exam, a lab test, to determine whether the person has MIC-N amplification or not. So this is what I call a clinical variable. The MIC-N status is what I call a clinical variable, and it has a very profound impact on the prognosis of a person. Okay, all right. Let's do something similar for the high risk group. We're gonna do the same thing, except that in the x-axis, we're gonna use the high risk variable instead of the MICAN status. So we just copy this line here, paste it here, and we now see that majority of the patients with high-risk disease present MICAN amplification. Only a very few number of the high-risk individuals do not have MICAN amplification. And in the non-high-risk group, we do not have any patient, we do not have patients with MICAN amplification. So we can conclude here that MICAN is it seems like it's specific to the high risk group, or it accounts for a lot of the probability of a patient to be diagnosed as a high risk neuroblastoma patient. So comparing this figure to this figure here, I see that it's removing the NAs, but I want to try this out because it seems like it's missing the, oh. How did it not? Oh, okay. Now it's filling it's filling with the high risk variable now. So the colors are the high risk groups. And again, we can see that MICAN accounts. Again, we can see that in the high risk group, we have a high expression of the MICAN gene. Or in other words, that the high risk status correlates positively with the MICAN expression. All right, any comments or any concerns or anything that you want to mention before we move on to the survival analysis part? Okay. Does anyone know what we are going to, what a survival analysis tells us? Has anyone heard about a survival analysis before? Let's just do a very brief Google search for a survival analysis. Survival analysis is concerned with studying the time between entry to a study and a subsequent event. Originally, the analysis was concerned with time from treatment until death, hence the name, but survival analysis is applicable to many areas as well as mortality. I always like to read the Wikipedia articles. It's a branch of statistics for analyzing the expected duration of time until one event occurs, such as death in biological organisms and failure in mechanical systems. Kaplan-Meier curves. That's the type of analysis that we're going to see today. Definitions of common terms in survival analysis. The following terms are commonly used: event, death, disease occurrence, disease recurrence, recovery, or other experience of interest. Time, the time from the beginning of an observation to an event or the end of the study, or the loss of contact or withdrawal from the study. Censoring, censored observation. Censoring occurs when we have some information about individual survival time, but we do not know the survival time exactly. The subject is censored in the sense that nothing is observed or known about that subject after the time of censoring. A censored subject may or may not have an event after the end of the observation time. Survival function, the probability that a subject survives longer than time t. Okay, I think we have had some introduction to survival. So the data frame that we are looking at, the GSC 62564, has survival information on it, as well as gene expression and the phenotype scoring. And so the survival information is with the information that I called the metadata last week. Okay, so in order for us to do the survival analysis, we need to do some processing on a couple of variables of the data set. The first variable that we're going to modify is the OS underscore bean. That is the overall survival variable. So we need to make the overall survival numeric instead of character. So we can ask R, what's the class of the overall survival underscore bean? And it tells us it's a character. I need to make it numeric. And let's also ask R. Let's also ask R to print this variable for us. There's 498 status for this variable, right? So for this patient, they died. That's what the event means, right? This patient did not die. This patient did not die. This patient did not die. Okay. So what I need to do here is I need to construct this OS underscore bean underscore numeric. And what I need to do is I need to make this event a numeric variable. And in order to do that, I am using a if-else statement. So what this entire chunk is going to do is it's going to make the word event 1, the word no event 0. So I can copy this entire chunk and I can paste it here. It's complaining that it could not find this function, this percent greater than percent. So I need to load this library called Mediter. That's the library that contains this operator or this function. And you can see that I called this function. I should have called the function, I should have loaded the library at the very beginning. But because I did not, now I have to do it. Okay, let's try running this again. I'll go back to this command. So if I hit enter now I was able to run this chunk, these commands, and I was able now, hopefully, to create this OS underscore bean underscore numeric variable using the dplyr mutate function. Let's take a look at this object. This object. Well, this object, I did not create it now. What it is different now, it is that it's going to have another column called OS underscore bean underscore numeric. And let's use the function view here. I told you that I like RStudio better because of, one of the reasons is because of this view function, how it behaves here. So this is what the data frame looks like when I use the view command. If I go all the way to the right, it reaches the limit of between 1 and 50 columns. What I can do is I can go now all the way to the right. So I am now looking at the last column of the data frame. And the last column of the data frame is the one that I just created in the terminal here when I used this command here, this line of code. And that line was just this one here. And so wherever I have one here, I had event before. And again, we did that using the if-else statement, and you can see the syntax for that in this line. Okay, we can now ask what is the class of this OS underscore bean underscore numeric, because you see that here I am making it numeric because it is right now here in the R environment, it is not numeric. So let's ask R what class this R2 underscore GSC metadata and OS underscore bean underscore numeric, this one, right? Which class is that? It's a character. And that's why I have to also make it numeric. If I go back to this command here and I ask R again, which class is this variable? Now it's telling me it's numeric. This step now is to do the same with the event-free survival. I'm not gonna do this, or actually I'll go ahead and do because I'll just copy and paste. It updated the, I'm gonna close the data frame. And I also need to make the EFS underscore bean underscore numeric. I also need to make it numeric. Okay. Now we come to the survival plots. We are going to need to load this library called survival. The first thing that we have to do, we need to basically create a model that is going to calculate survival probabilities for us. And the way that it's going to calculate survival probabilities, it's going to use the information that is stored in this variable OS underscore day and the information that is stored in this variable OS underscore bean underscore numeric that I just modified, right? This variable was there in the OS underscore bean, and then I modified it so that it could be numeric. And now it's the OS underscore bean underscore numeric variable. Okay, I want to show you what the OS underscore day looks like. And to do that, I'm going to copy the name of this data frame. And I'm going to paste it here. And I'm going to ask R what the OS underscore bean, not underscore bean, underscore day, what it looks like. And R is telling me that it's a bunch of numbers with quotes around these numbers. And that's the reason why these numbers, although they should be numeric, right now they are not numeric, and I can pretty much tell that they are not numeric because they have quotes around them. And so what I'm gonna do to show that to you is I'm gonna type class, and then I'm asking R, what class does OS underscore day has? R is telling me that it's a character, it's not numeric. But I am going to tell you that this variable also needs to be numeric. And so that's why we need to run this line here. Sorry. No, that actually I could have done something like this, but in this case, I am making the variable numeric as I calculate the model, as I calculate the survival probabilities here. I did not mention to you, but here I'm using this surfit function from this package called survival. And in the surfit function, we have this surfit argument, and that's the argument that's taking the OS underscore day as numeric. Okay, we need to make the OS underscore day numeric so that this works out, because if I do not put the as dot numeric, it's not going to work. The other part of this code that I need to include is this variable here, but I already showed to you what this variable looks like, but I can always show it again. OS underscore bean underscore numeric, and not the class. On C, the vector, the actual vector. So it's a vector of numbers zeros and ones. Zeros for individuals that did not have an event, and ones for individuals that did have an event. And so the variables that I want to compare the survival of are the high-risk variables. So I want to compare the high-risk group with the low-risk group, and I want to know what the survival probabilities are for each one of these groups. And of course, the data that we are analyzing is still the R2 underscore GSC 62564 GSPA metadata. And because I explained all of that to you already, I'm going to copy this and paste it here. Let's check this fit underscore OS risk, fit underscore OS underscore high risk. So there is this call portion here, this call part, and here it is telling me that this serve function is a formula. It's a formula where we have the OS underscore day and OS underscore bean underscore numeric. And we have the high risk. We're using the high risk variable. In the bottom here, I can see that the high risk patients, sorry, the patients that do not have high risk disease, they are 222. The patients that do have high risk disease, they are 176. There's much more events in the high risk group compared to the non-high risk group. The median, it seems like it's the median number of days. The median number of days survived for the high risk individuals is this number, and for the non-high risk, it doesn't show. It does not show up. It's not non-applicable. And so I'm not going to go through the confidence intervals here. So this is what the survival model is going to look like, okay? So we just generated the survival model, and that's how R calculates for us the survival probabilities. What we're going to do now is we're going to calculate this graph, which is a Kaplan-Meier graph. It shows the survival probability in the y-axis by the time in the x-axis. Okay, so this is the syntax for that. We need to use the model that we just constructed in the previous chunk. The data is the same data set. I am setting the risk table here to true. The risk table is basically these values here. And then I am setting the p-value to true because I want R to calculate a significance p-value for me. I want to know whether the survival probability is significant or not between the two groups. And then the p-val dot coordinate dot coord is the coordinates of the p-value. So I'm going to go ahead and copy. I'm actually going to need the ServMiner library. So I will load that. And I'm going to go ahead and plot this survival curve. So we have in the x-axis the time in days, all right? And in the y-axis, we have the survival probability. The high-risk group is the group that shows the lowest survival probability, meaning that, unfortunately, kids die more frequently in this group than in the non-high-risk group. The survival probability of the non-high risk group is quite high. Not a lot of these patients, not a significant number of these patients die over time. But you can see here that the difference in survival between the non-high risk and the high risk group is very significant by the value of the p-value here. So we can change the coordinate of the p-value. Let's change it to, say, 1500. I only changed the x coordinate. I actually wanted to change the y coordinate. Let's make it 0.7. So now you can see the location of the p-value changed here. I don't know if the I do not know what's going to happen if I set the risk table to false. Oh, okay, that's what I imagined. You can see here that we do not have the risk table being shown or the number of patients that are at risk as we did when we had set the risk value parameter to true. Okay. Why don't you guys try do you guys want to try plotting this figure? First of all, let me ask, are you guys following me? How is it for you guys? How are you guys feeling about all of what we are doing?
I think I'm like doing okay. Like it's taking a while for the thing to load, but I think I kind of get it.
Okay.
But yeah.
Do you think I am going too fast?
But no, I just think like I just need some more time to like process the information. But I think you're doing perfect. Yeah.
Okay. All right. Victor said he's been able to follow at this time. Is anyone not able to follow what I am doing here or not understand what I'm doing here? And does anyone want that I explain anything one more time? Is everything fine for everyone? Okay. Why don't you guys try to repeat this plot here? Maybe I should give you like 3 or 4 minutes to try to repeat this plot and try to identify what the difference is between this plot here and the plot, the second plot, the second survival plot. 3 minutes. Try to repeat this and think about what the difference is between the plot from above and the second plot. Alexandra. Our studio cannot find ggserve plot function. Did you load? Did you load the library serve miner?
Yeah.
Is it from serve miner or survival? It's from serve miner. Are you sure? Do you want to share? Do you want to share?
Yeah, sure.
Can you put library, open parentheses, close parentheses, and then serve miner? Can you, yeah. Did it go
Thank you.
through?
Yeah, it loaded.
Okay, yeah, it was just some, oh, I don't know exactly what it was. Okay, does anyone want to? Does anyone want to explain what the difference is between this plot and the one above?
What has percentages?
Yeah, this one has percentages instead of the absolute numbers per groups. So for example, here in the high risk group, instead of 176, it fell down to 46, which is 26% of the 26% of the 26% in regards to time zero. It decreases from 100% to 26% and then to 2%. Okay, I would like you guys to try and generate the EFS plot, because this one here used the OS plot. Does can you guys go ahead and try to use the and plot the curve for event-free survival? Okay, in order to plot the event-free survival, we need to find the fit underscore EFS object. It doesn't seem like we have constructed this object. I had the feeling we had. Okay, we can do it very quickly. Let me open an R script here. So we are going to construct we have to construct I'm going to show you here, the EFS object. And so this is going to be the EFS day. And well, this EFS, I just want to show you guys that this EFS, EFS underscore day variable exists. So you see it there, right? And the reason why I know that it exists is because we used the OS underscore day before, right? So now it is asking us to plot the EFS. We also have this variable called EFS underscore bean underscore numeric, but I will double check that it exists. So it is here. And then we are going to compare the high risk groups. So this should remain the same. This should remain the same. So now I'm going to take this line and paste it in the console. And this basically constructs the fit EFS underscore high risk. And now I can, oh, sorry that I was not sharing my screen. You see my screen? Okay, I will have to repeat everything. You see my screen now, right? You still do not see my screen?
I don't see our studio.
Don't know what's wrong. Do you see my RStudio now?
Yeah.
Okay, great. So we were here in this part where I say have students generate the EFS plot. And so in order to generate the EFS plot, we basically have to have the fit EFS underscore high risk object. We have to have something like this, right? So I'm copying this and I'm bringing it here. And I'm going to call this the EFS underscore high risk. So this variable, we saw that this variable is for the overall survival. Now I want to calculate something for the event-free survival. So this variable here is I want to use the EFS underscore bin underscore numeric. I still want to do the comparison for the high risk group and using the same data frame. What I'm going to do now is I'm going to see if these variables, if they do exist, the EFS underscore day, it exists in the data frame. I also want to check if the EFS bin numeric, it exists. And so we should be good. So if I copy this and paste it in the console, it should work. Apparently it did because I can even, so if I ls, if I list, right? It shows me that I have the fit EFS and the fit OS object. I can also come here in the environment screen. The fit EFS object is here, as well as the fit OS underscore high risk object. Okay, so now we have the survival model, and therefore we can go ahead and plot the survival curve. So I'm going to paste it here. We only need the EFS high risk object. Okay. Let me see now. So we were able to generate the Kaplan-Meier curve for the EFS analysis, the event-free survival analysis, the event-free survival, event-free survival analysis. That's the way to put it. So this is the high-risk group. It has a much lower survival probability than this is the high-risk group. It has much lower probability compared to the non-high-risk group. The p-value is very significant. All right. Okay, so this is done. I'm not going to save this or anything. I'm gonna come back here. And that's it. The next part is hypoxia in the tumor microenvironment. I think it's been an hour since the beginning of the session. Let's go ahead and do the 5 minutes break. Is it okay? Let's do the 5 minutes break and then we'll come back here in 5 minutes. All right, I'll come back in 5 minutes. All right, everyone. Let's move on now to hypoxia in the tumor microenvironment part. This is the subject of the subject area of the mini project that we have. If people want to do a presentation on the project, just let me know. Maybe you can use one of the figures that we're going to generate now, and you can put together a small presentation for Friday. Okay. So we want to establish the first thing that we're gonna do now is try to establish a relationship between the neuroblastoma high risk status and hypoxia. Hypoxia is a condition of low oxygen concentration that is established in the tumor microenvironment when the cancer progresses. And the reason why hypoxia it establishes in the tumor microenvironment is because the metabolism of the cancer cells are much faster than the metabolism of normal cells. So the HIF1 alpha is the transcription factor that is sensitive to oxygen levels. HIF stands for hypoxia-inducible factor. It is a single gene. And we are going to do some analysis with this gene. As you saw for other variables, we have to also make this variable numeric, okay? Because it's the gene expression value. We can run this part here is to run a statistical analysis because I want to know whether the difference, whatever the difference that exists between the high risk and the non-high risk group, I want to know if that's significant or not. Apparently it is significant. Okay, I used this compare means function. We compared the HIF1 alpha expression in the group that had in the high risk group with the non-high risk group. The p-value is 0.00032. This p-value is significant. The adjusted p-value is basically the same because you only have one comparison being made here. The method that was used was the t-test, and we spoke a little bit about the t-test at the last week. Okay, now we are going to generate this plot here. We are again going to use the ggplot function, the data frame. We're going to use again the AES function with the x-axis as the high risk, the y-axis as HIF1 alpha expression, and the colors are going to be the high risk variable. We will have to use the geom_plot argument here because we need to plot it as a box plot. And then we are going to use this stat_compare means argument because I want this to include the results of the t-test, just as you see here in the figure, and the theme_line draw is the theme of the background that is in the figure. So if you compare, for example, with this theme, they're different, and the way that we specify this background is by using this theme_line draw. So I'm going to go ahead and copy all of this and paste it here. There you go. We have so this is the HIF-1 alpha expression in the high risk and non-high risk groups, we can see that is significant. It's a significant difference. What we see in this plot is that the high risk group has a much higher HIF-1 alpha expression. Okay, HIF-1 alpha is on a single gene. Let's take a look at this hallmark hypoxia. Let me do a very brief Google search here. Let's look for msigdb. msigdb gene sets. Let's take a look at this. There is this GSEA package. Let's take a look at here. It's so this page is the gene set enrichment analysis page, the GSEA page. This says browse human gene sets. This is from UC San Diego and the Broad Institute. So there are collections, msigdb human collections. Let me click on this. Okay, I like this. Let's take a look here. The 35,000 gene sets in the human molecular signatures database, so that's what the msigdb is, are divided into 9 major collections and several sub-collections. See the table below for a brief description of each and the human msigdb collections details and acknowledgements page for more detailed descriptions. See the latest msigdb release notes. Okay, so hallmark set genes, positional. So H stands for hallmark set genes, C1s, positional gene sets, curated gene sets, regulatory target gene sets. So there's a bunch of collections of genes and there's a number of gene sets. So in this collection, I would say that this is a very famous collection of gene sets. Apparently there are 50 gene sets here. Let's take a look at these 50 gene sets. Okay, I believe that these are the 50 gene sets. The hallmark hypoxia. Okay, I was looking for the hallmark hypoxia. Let's take a look at this. Human gene set, hallmark hypoxia, standard name, brief description, related gene sets. Apparently the members here are 200 genes, and I think so. Let me remind ourselves. I should probably put this in a place that is more analysis, more obvious maybe. I'm going to open this again. So this is the gene set that we analyzed last week. You can see here that I have a bunch of hallmark genes. Hallmark hypoxia is one of them. Hallmark hypoxia is one of them. Where's my hallmark? Hallmark hypoxia should be here somewhere. This one here. You can count and you'll see that there are 200 genes here. But one thing that I noticed this morning was that the HIF-1 alpha gene is not here. HIF-1 alpha is not here. So when I do the search, it doesn't find it here, but when I do the PGK1, it does find it there. The PDK1 is also found there, but HIF1 alpha is not in this list. And okay. All right, let's go back. I'm gonna close this. I'm gonna close the MSigDB. So I just wanted to show you guys where I got those gene sets from. And because this hallmark gene sets, they're very famous. That's why I decided to use a gene set that is a phenotype of hallmark hypoxia, right? It's basically a gene set that characterizes the hypoxia state, not only a single gene, but a gene set, okay? And so it is one of the gene sets. It is a group of genes that define the response to hypoxia, and we also must make it numeric in the data frame. And now we can plot hallmark hypoxia. Can anyone tell me, or actually by looking at this figure and this figure, can anyone tell me what these figures tell us? Can anyone summarize these figures for us? Nobody can summarize these figures for us? Okay, I will do it. So we have higher HIF1 alpha expression in the high risk group here. Higher HIF1 alpha expression in the high risk group, whereas here we have higher hypoxia scores, higher hallmark hypoxia phenotype scores in the non-high risk group. And if you do the statistical analysis, you'll see that this is significant. This is significant. So it is a little bit counterintuitive that HIF1 alpha is higher in the high risk and hallmark hypoxia is higher in the non-high risk group. So that's why I mentioned that HIF1 alpha is not in the hallmark hypoxia. So that's why I drew these conclusions here. The conclusions about the HIF1 alpha and the hallmark hypoxia analysis. So the transcriptional program activated by HIF1 alpha is different than the hallmark hypoxia program. Because HIF1 alpha expression is higher in the high risk group and the hallmark hypoxia score is higher in the non-high risk group. They are kind of antagonistic, right? So this hallmark hypoxia program does not seem to be led by HIF1 alpha activation. The hallmark hypoxia gene set does not have HIF1 alpha. I do not know exactly how hallmark hypoxia was generated, but depending on how it was generated, it used genes that correlated positively or negatively with HIF1 alpha. So hypoxia causes increase in HIF1 alpha and an improved survival through the upregulated genes and a worse survival through the downregulated genes. So the next question that comes to my mind is whether the hypoxia activation is also a HIF1 alpha activated program. And we're gonna have a better idea about that. Let me first discuss this with you, and then we can do the plots. So the hypoxia downregulated, these are we discussed this gene set last week. these are the genes that are downregulated in vitro by hypoxia. Okay, so we treat the cells with hypoxia. The cells have genes that are downregulated by hypoxia, and the cells have genes that are upregulated by hypoxia. So the genes that are downregulated by hypoxia, these genes happen to be much more active. They're much more active in high-risk disease. So can anyone tell me if this means that hypoxia downregulation is a gene set of good prognosis or bad prognosis? Alexandra said bad prognosis, that's right. Hypoxia downregulation is a gene set of bad prognosis because people that have high-risk disease have much more higher phenotype scoring compared to people that do not have high-risk disease. Let's take a look at the statistical analysis. That's very significant. So yes, this gene set is a gene set that has a terrible outcome for the patients. And in fact, one thing that I am not showing here that is probably very interesting to show is that in the high-risk group, this gene set is also in the high-risk group, this gene set is also shows also very significant bad prognosis. So also when the patients have high-risk disease and they do have a high scoring of this gene set, they also do show worse prognosis. Now, the other way around happens with the upregulation of the hypoxia targets. So when we treat the cells with hypoxia, some genes go up, some genes go down. We were just discussing the effect on genes that go down. Now on the genes that go up, if we look at the expression of those genes and compare non-high risk with high risk, non-high risk have much higher expression of, higher scoring of this phenotype, much higher hypoxia upregulation phenotype score. So what does this mean? This means that hypoxia, it's the conclusion that I put here. Hypoxia causes increase in HIF-1 alpha and an improved survival outcome through the upregulated genes, and a worse survival outcome through the downregulated genes. I do not know how genes that are downregulated by hypoxia are actually upregulated in the tumors, because it seems like these genes have a much higher expression in the high risk tumors. So that's something that I think is really interesting. And by the way, these conclusions should come after the upregulated and downregulated gene sets. Okay, so I think this is the main conclusion here. And I think that in the literature, I do not see people investigating so much which genes are activated by hypoxia and which genes are downregulated by hypoxia, but it seems like this is a path that is worth pursuing, that's worth investigating, it seems like. Do you guys have any questions or any comments about this part? Yeah, so the conclusion here would be that we need to understand better the genes that are activated by hypoxia and the genes that are downregulated by hypoxia. Okay, I will have to run this chunk here because I need to do some processing with these characters, the spaces, the dots, the commas, and so that's why I'm running this line here, this line of code. And by the way, the hallmark inflammatory response, we also have higher phenotype scores of hallmark inflammatory response in the people that have non-high risk disease compared to high risk disease. That's also significant. Okay, let's continue in this part. So right now I think we kind of understood that there is an impact of hypoxia in the tumor microenvironment. There is an impact for this gene, particularly in the tumor microenvironment. And so far, in the one data set that we're analyzing here, it seems like that this gene has a bad prognosis or a bad impact in the tumor microenvironment. And I think that is very consistent with the literature. So let's take a further look at the survival analysis. At the survival analysis of the expression of this gene. Let's load this package here. What we're doing now is we're going to create this quantile variable. Okay, let's create this. The reason why we are creating this quantile variable is because we are dividing the HIF-1 alpha variable into two quantiles. Basically, we are taking all of the HIF-1 alpha expression values. And which HIF-1 alpha expression values I'm talking about? I'm talking about these values here. So the first patient has an expression of 83, the other patient 86, 77, 95. What this part here is doing is it's ranking these HIF-1 alpha score values, and it's taking the median. The median is the number at which we have 50% above that value and 50% below that value. So for example, let me see if I can order or maybe sort. Let me sort the HIF-1 alpha values. Okay, I just sorted the HIF-1 alpha values, and you can see that the minimum is like 20, and then 25, 26, 27, 29, 31, all the way through the highest HIF-1 alpha expression is 271. Let me do something even better. Let me check what the median. It's 71.5955. 71, it's here, 71.59. 71.59. Should be probably one of these. Probably one of these. So in the first quantile, we have the values that are smaller than the median. And then in the second quantile, we have the values that are greater than the median. And I hope that I stated those values. I hope that I stated those values accordingly. Otherwise, we'll have a chance to confirm that in a moment. So we just looked at the HIF1 alpha variable. Let's now look at the quantile variable. So let's take a look at the quantile. Not the median. I do not want the median. I want to just take a look at it. So, okay. I'm going to sort. No. So if the HIF1 alpha expression of this individual here was bigger than the median, and we know that the median was 71, that's why it was assigned 2. Same thing with this one, same thing with this one, and so on and so forth. So for majority of them, a good number of them is number 2, because these individuals all have HIF1 alpha expression values bigger than or greater than 71.59. So I hope that gives you an idea of what this is doing. Now, what this next line does is it makes the quantile a factor. Now, with this next chunk here, what we can do is we can take a look at the quantiles. Remember, guys, each one of these dots is a tumor, right? So you can imagine a line here crossing at the very border of the red and the blue dots, and that line is the median, right? So everything that is above the median is quantile 2. Everything that is below the median is quantile 1, because well, that's the way that the entire function partitioned the HIF1 alpha variable. Everything that is below the median is quantile 1. Everything that is above median is quantile 2. Okay, so that was to show that. Now we are going to run the survival analysis using overall survival and DOS underscore being underscore numeric, using the quantile variable that we just created, right? So remember that before we were comparing the high risk variable. The high risk was also composed of 2 categories. We just constructed the quantile variable with also the 2 categories that we are showing in this scatter plot. So let's run this chunk. And let's run the survival analysis for the HIF1 alpha gene. Okay. Remember that this is for a single gene, okay? And you guys should remember that quantile 2 is the quantile that has the highest expression of HIF1 alpha. In other words, these are the patients that have higher HIF1 alpha expression, correct? You can see that here in the scatter plot. Higher expression of this HIF1 alpha gene. These patients, unfortunately, have lower survival probability compared to the patients that have, compared to the patients that belong to the quantile 1 which means the set of patients that have lower HIF-1 alpha expression. So this again shows the bad prognosis associated with higher expression levels of HIF-1 alpha, basically. Okay. We could do the same thing or something very similar for the event-free survival. I'll let you guys do that. And we have, I need to figure, I will remove this line from next versions of the notebook, of the code notebook, but for now we have to run this. It just has to do with the way that I wrote this notebook. Later I'll deal with this extra line of code. So now let's move on to the last part of this notebook. That is the relationship between HIF-1 alpha expression and the age at diagnosis variable. Sorry that I didn't ask this before. Were you guys able to generate the survival analysis for HIF-1 alpha? Or no? Alexandra said yes. Anyone else? If you want, I can, if people want, I can try to spend 1 or 2 minutes helping. You can also create a breakout room so that the TAs can try to help you guys. Victor said that he also was able to generate the survival curve. All right, there's going to be, so I have more exercises in the exercise session of the website. I think there's going to be a question about there are going to be a couple of questions about the survival analysis, and I think there's going to be one about HIF-1 alpha. Okay, let's now go ahead and switch to the HIF-1 alpha relationship to age at diagnosis. First thing that we're going to do in this part is again to make the age at diagnosis numeric. Actually, I do not need to do this. This is for something else, but yeah, let's go ahead and it will not hurt. Make the age at diagnosis numeric. The maximum age at diagnosis is almost 9,000 days. The minimum age at diagnosis is 0, which maybe it's an error, and then it's because of an error that it's telling us that the minimum is 0. I do not trust this number there. Now we are going to use the entile function again to divide the age at diagnosis into quantiles again. Let me know if you guys need that I try to explain this again. I explained the idea of the entile function. Let's take a look at the age underscore quantiles. And so the object changed the name. Right now it's called R2 underscore GSE 62564 underscore GSV underscore metadata underscore spaces underscore survival underscore age. Sorry that this is a very big name, but what I want to do here is I want to take a look at the age at diagnosis, age underscore quantile. That's the one that I want to take a look at. And so I see here that we do have 3 quantiles. So I divided the ages in groups of 3. I can use another function that I always use. What is it called? Cross cases, cross values. I forgot the name of What the name of the function. I'll do a Google search here. I want to see how many of each age quantile I have. XPSS. Yeah, it's this one. It's cross cases, I think. So I'm just going to load this library. XPSS. It looks like I'll have to install. The XPSS. Okay, so what I want to do is I want to take a look at how many individuals we have in each age quantile. So the way that I do that in the cross cases is I specify the data frame, which is this one here. And then here is going to be the name of the variable that I want to count, which is this one. Yeah, so as we could be imagining, what the function, which function, this function, the entile function did was it split the the values of the age at diagnosis, right, into three equal quantiles. And how can I tell that they are equal? Because they all have 166 individuals, and the total cases is 498, as it should be. Okay, all right. I have to make the age quantiles factor. I want to see what it is now. So it's this one, and I'm gonna make age. Why it's not? What's wrong? Something seems to be wrong. Okay, it's just not auto completing. For I don't know why it is not. I just want to know the class of. Oh, there you go. Age quantiles. There you go. Okay, I want to ask it what the class is. It's an integer, and I need to make it factor. We make it a factor, and when we make it a factor, after we make it a factor, we can generate the plot using that chunk. And there you go. Let's take a look at this figure here. So for the patients that are at the age quantiles 1, it's a very significant difference. And the change in actually the number of counts of HIF1 alpha in the high risk group is much higher than the non-high risk. And you can see that although that it's still qualitatively higher in the older older kids, it loses its significance, and that change is not so drastic. whereas in the oldest kids, that difference is not significant anymore. So this suggests that there is a relationship between HIF-1 alpha expression and the age at diagnosis and the high risk group. So the younger the age at diagnosis, the more severe impact we have of HIF-1 alpha in the high risk group. So I do not know if this the high risk disease is severe at this age than other ages. That's actually a good question. That may be something that we can investigate. But apparently there is a relationship between HIF-1 alpha and age at diagnosis and the risk category. There's apparently an association between age at diagnosis, HIF-1 alpha, and risk category. Okay, we're only 6 minutes before the end of today's class. Do you guys have any questions or any comments? Nobody has a question or a comment? Okay, I think the next plots are pretty similar. The main scientific conclusion that we would draw from this notebook is this, that there is a relationship between HIF-1 alpha expression and the age at diagnosis and the risk category. So that's it, I would say, for the scientific discussion. Now, if we go to the website, you guys are going to see that we have the exercises tab, and I put a couple of questions here. The first 3 questions are actually the question that we had. We did some investigation last Friday, right? So the relationship between hallmark inflammatory response and hallmark hypoxia, that they have a positive correlation, also a positive correlation between hallmark inflammatory response and hypoxia upregulation, and a negative correlation between hallmark inflammatory response and downregulation. And now there are a couple of other questions here. So let's actually go ahead and try to answer, for example, this question here. So the question 5 is, which gene expression group has the worst survival probability? Is it the high HIF-1 alpha expression or the low HIF-1 alpha expression? Yeah, we just did the survival analysis, and we saw that high HIF-1 alpha expression has worse survival probability or lower survival probability, and that's what this question is asking about. Which phenotype score group has the worst survival probability? Is it the high hallmark hypoxia or the low hallmark hypoxia? Yeah, it's the low hallmark hypoxia. You can also understand this by defining that the low hallmark hypoxia group has lower inflammatory response score, right? I don't know if you guys wanted to talk a little bit about that or discuss that a little bit, but that's it. And question 7 is almost the same thing. Which phenotype score group has worse survival probability? The high hallmark inflammatory response or the low hallmark inflammatory response? It is the low hallmark inflammatory response, right? Has worse survival probability because if the tumor does not have inflammation, it means that the immune system basically cannot the immune system can basically not take care or not take a very good care of beating the tumor, right? Okay, this one, I don't know if you guys can answer this one, but let's try this one as a last one. Plot the survival curve of the MICAN status variable. Which MICAN status has worse survival outcome? Do we have worse survival outcome in the individuals with MICAN amplification? Do we have worse survival outcome in the individuals that do not have MICAN amplification? Or do the group that has unknown MICAN status? Which one is the worst survival outcome? Claire, what do you think? Eric, what do you think?
I'm honestly not sure.
Sorry?
I'm not, like, if I were to answer the question, I wouldn't know how to.
Okay, do you know if MICAN amplification is good or bad? Let me see.
No.
MICAN amplification is bad. That's fine. Let me see if I find a figure to show that here. MICAN amplification is bad. Well, you can imply that here when you have high risk disease, majority of people with high risk disease also have MICAN amplification. You can see that here. So MICAN amplification is bad. And so all of that to say that individuals with MICAN amplification have worse outcome.
Oh, okay.
Yeah.
Got it.
Yep. All right, guys. Thank you so much for participating. Thank you for participating also in answering these questions. We are always here. Just let us know if you have any questions through email or through the Slack channel. If you do not have questions or if you do not need to talk to me, thank you very much for joining. Have a good night. Enjoy the rest of your night. I'll see you again on Wednesday. Thank you.
Wait, I have a question. For the notebook, you said we're supposed to upload it somewhere, or we're supposed to upload it somewhere?
Yes. Let
Okay.
me.
Yeah.
It's in the lab notebooks folder. I can share my screen. Do you have access to?
Yeah.
You
Yeah, I do.
here. So you just put like it's week 2, day 1, and then your name. That's it.
Oh, so
What's
wait.
What's
What like am I supposed to make like I made my own copy? It's just
in your local machine?
yeah, I just made my own copy and did it from there. Was I supposed to do it like because
You can do
I
it. You can do it in the shared drive. The purpose of the shared drive is so I can take a look at your guys' progress.
oh okay.
Yeah,
All right then.
just upload it here.
Okay, thank you.
Mm-hmm.
We'll do that.
Sure. All right. Thank you, Atenish.